Segment 1. Solid, liquid, gas.
Do you want my lolly? Yes, please.
On warm days, a popsicle can be the perfect treat. It's made by freezing flavored water into ice. As you eat it, the ice melts into liquid.
Have you been to Alton Towers? Yeah, I went on Tuesday. Did you go on a whirly? Oh, Jay!
The liquid will evaporate into a gas and become part of the air. Adding enough heat energy to most materials makes them change from solid to liquid to gas. Water is a good material to illustrate changing states. It doesn't require extreme temperatures to change from solid to liquid to gas.
Just watch.
Here it is in liquid form. With no shape of its own, it takes on the shape of its container. This water is about to be frozen into a huge block of ice. Changes will occur deep inside its molecular structure. Like all materials, water is made of molecules. In liquid form, these molecules move around quickly. As the temperature is lowered, the molecules slow down and bond to form a rigid structure. This is ice. Ice is a solid, and like all solids, it has form and hardness, which helps it hold its shape. Duncan Hamilton is an ice sculptor. He uses very sharp tools to cut through the large block of ice. Making the sculpture in a warm studio is a race against time because ice stays in solid form at a temperature of 32 degrees Fahrenheit or 0 degrees Celsius or below. If enough energy is added to the ice, it starts to melt into water. Its molecules begin to move around faster, which makes the rigid structure disappear. Sometimes a sculptor uses heat to deliberately melt the ice. At a temperature of 212 degrees Fahrenheit or 100 degrees Celsius, the ice turns to liquid and then to steam, the gas form of water. When water turns to steam, the molecules move even faster. This process works in reverse, too. Steam will condense to water, and water will freeze to ice. Most materials change state from solid to liquid to gas, but the amount of energy needed to make the change is different for every material. Take iron, for example. It's hard to believe that when this iron bridge was being made, all these pieces were liquid. They were made at this foundry about 100 years ago. This metal goes in as solid mass and comes out as a liquid. It melts because enough energy is added to make the molecules of metal move rapidly. The liquid metal flows and can fill the inside of a mold. After only a few minutes in the mold, the metal cools and changes into a solid. It's been cast into a new shape. The furnace is over 2,000 degrees Celsius, and it must be cleaned. Water sprayed on the leftover materials cools them down. The water changes state from a liquid to a gas. The heat from the materials is transferred to the water molecules, making them move extremely fast. Solids can change to liquids and back at a much lower temperature, too. It all depends on the type of molecules. It happens at the candle makers. This liquid wax is hot, but not as hot as liquid metal. The wax becomes solid at room temperature. As a candle burns and heat is added, the wax changes to a liquid again. No matter what the material, changing states is about adding or taking away energy from the molecules. Solids melt to make liquids. Liquids boil to make gases. If it's an ice sculpture you're creating, make sure it stays frozen solid, or all your work will be lost.
Try this activity to complement solid, liquid, gas. In a bowl, slowly add water and a few drops of green food coloring to 1 box of cornstarch. Mix all ingredients with your hands until they form a solid ball. Describe the properties of this substance. Segment 2. Pressure.
The human body lives under pressure. The pressure of Earth's atmosphere pushing down on top of it. But it's okay, because we're used to it. In fact, we rely on it. What happens to the human body when it travels to places with different pressure? Like underwater, where the pressure of the atmosphere and water are combined. Or at high altitudes, where there's very little air pressure. Or in space, where there is almost no pressure. Pressure is force applied to a surface, such as the pressure of Earth's atmosphere. Air doesn't weigh much, but when it's stacked up more than 50 miles high, there is about 14.7 pounds of force pushing inward on every square inch of your skin. At sea level, this pressure is called 1 atmosphere of pressure. We're so used to it, we don't even notice it. But when we go underwater, the pressure increases quickly, since seawater weighs a lot more than air. Sean is a professional diver. At 180 feet below the water, Sean's body experiences more than 6 times the atmospheric pressure of sea level. If he dives too deep, the pressure could be great enough to crush him.
Once a year, we have a contract with the local canneries to clean and maintain their pipelines, which is at about 180 feet on the bottom, and at which point your diving becomes a little more risky at that depth. It's dark and it's dirty, and it's as dangerous as you can make it.
The air Sean breathes underwater is affected by one of the basic principles of pressure. If you increase the pressure, the volume or the space materials take up decreases, but the density of the molecules increases. Density is the amount of matter in a certain space. If the density of air is increased, there will be more molecules of the different gases that make up air. If the density of air decreases, there will be fewer molecules in the same space. At 180 feet underwater, Sean takes a breath of air from his tanks. The air is under a lot of pressure. That means that the molecules of the different gases in the air are more dense than Sean's body is used to. One of the gases in the air is nitrogen. Breathing large quantities of nitrogen makes divers feel confused or disoriented, and too much nitrogen may paralyze or kill.
It can make you disorientated where you actually don't know what you're doing. You think you're doing something, but your movements are a lot slower, and it really affects your mind on how you perform underwater.
After 10 days of dives at 180 feet deep, Sean found himself in trouble.
I got to the surface, and probably within 30 seconds, I looked at my partner, and I said, there is definitely something wrong.
Sean!
As Sean rose to the surface and the pressure decreased, the nitrogen in his blood became less dense and expanded to form bubbles. One of these bubbles formed around his spine, paralyzing him from the waist down. Sean was sent immediately for treatment in a hyperbaric chamber. This is a pressure chamber that puts patients under the same pressure they were at when they were diving. Putting pressure on the nitrogen bubbles in Sean's spine should cause them to contract and be reabsorbed into his bloodstream. After multiple treatments in the chamber, most of the nitrogen bubbles finally dislodged, and Sean was able to begin learning to walk again. Deep-sea divers like Sean expose themselves to life-threatening hazards every time they dive because of the high pressure their bodies are under. It's the opposite on the highest point on Earth, Mount Everest. Here, the summit is 5.5 miles above sea level. Because there's so little pressure at this altitude, the air is about 1/3 as dense as at sea level. That means that with every breath of air, there are fewer molecules of oxygen than the human body is accustomed to. Ken Kamler is a high-altitude physician. He's been on 6 Everest expeditions, including one in 1996, when 9 people died in a single day.
Everest is a legend. It's not just a mountain, it's a legend. It has a tremendous history behind it. It's got a mystique. In addition to that, being the tallest mountain in the world, it's tantalizingly close to the limit of human physiology. So you're climbing in an area where physiologically your body is not able to adapt. Human beings can't adapt to an altitude above 17,000 feet. That's already half the air pressure that you have at sea level, and the summit is 1/3 the pressure that you have at sea level. So you're climbing in a range of very much reduced oxygen pressure. The body's not used to that. The body's not really equipped to deal with that.
Preparation for an ascent on Mount Everest takes months. And it takes 10 days for the climbers themselves to walk into the mountains with all their supplies.
The body has to acclimatize. That's a process that takes several weeks actually to be fully completed. It starts out just by breathing deeply and gasping for air. That's when people feel short of breath because they're trying to get more oxygen. And after a while you get used to that and you begin to breathe easier because your body brings in other processes such as increasing the number of red blood cells which carry oxygen. It makes it easier for you to transport the oxygen to your tissues. Those processes take weeks.
Dave Hiddleston is making an attempt to reach the summit. He's spent months adjusting to the climate and altitude, but now he's climbing near what is called the death zone, where the oxygen density of the air is only 1/3 of that at sea level. Even using bottled oxygen, getting enough to the body is almost impossible. Depriving the body of oxygen causes disorientation and damage to tissues. You can't stay in the death zone too long. On this day, Dave Hiddleston is having too much trouble breathing, so he's decided to turn back before reaching the top.
Everest is not the hardest mountain in the world to climb. But the difference is when you're doing that climb at 29,000 feet and you have 1/3 as much oxygen and the temperature's 30 below zero and you've been out for 16 hours and you've only had a half a glass of water to drink in the past 24 hours, that becomes a daunting challenge.
The name Mount Everest has come to mean the greatest challenge. But there's another more challenging environment: space. To work and explore in space, humans must take their environment with them. There's no oxygen in space and almost no pressure. Without air pressure, the materials in our bodies become less dense. Liquids turn immediately to gas, and our bodies explode.
Of Mike, and you see me doing my spin around which way to go, which is...
Space exploration is possible only because we have figured out how to carry pressure. Spacesuits and spaceships are pressurized so the human body can function normally. Whether we swim beneath the sea or climb high in the mountains, pressure has an effect on our bodies. Pressure changes the density of the gases in the air we breathe. Too much or too little can be deadly. As long as we take enough pressure with us, we can go just about anywhere.
Try this activity to complement pressure. Pour a small amount of boiling water into a 2-liter plastic bottle. Immediately screw on the cap. Then place the bottle in a bucket of cold water. What happens when the water vapor from the hot water cools? Segment 3. Heat.
Heat is critical. Our very lives depend on it. But everything has different amounts of heat. If you could see heat as color, it might look something like this. In these pictures, white is hottest, then comes red, green, and blue. Black is coldest.
13 degrees. Just like it's pretty chilled now.
Our bodies, buildings, cars, all need to be kept at certain temperatures. Temperature is a measurement of heat. Not enough heat or too much heat, and they'll be damaged, even destroyed. But what is heat, and how can you measure it? Our bodies sense heat through our skin. Nerve endings help us feel heat, but they don't measure it very accurately. What feels warm to one person may feel cold to another. To develop accurate measurement, scientists had to learn more about heat. Heat is energy. It makes the molecules of all materials pick up speed. As these molecules move faster, more space forms between them and the material expands. If heat is taken away from the molecules, the material contracts. The basics of heat measurement were developed in the 16th century by a scientist named Galileo. He was studying the effects of heat, and he observed that as most things get hotter, they expand. When they cool, they contract. Galileo made an instrument that had liquid at the bottom and air trapped at the top. He noticed that when he heated the air, it expanded and pushed the liquid down. When he cooled the air, it contracted and pulled the liquid up. Galileo had made an early version of the thermometer. It demonstrated the effects of heat, but it didn't tell what the temperature was. For that, scientists needed a scale to measure how far the liquid moved. When you're designing a scale from scratch, where do you start? How do you decide where the top and bottom points should go? Scientists established one low temperature that was constant, the point at which water turns to ice. This became the 0 on the scale. Next, they needed a fixed high point. Again, the answer came from water. It always boils at the same temperature at a given altitude. Scientists divided the gap between the two fixed points, and they had their scale. But that's also where their troubles began. In the early days, there was no standardization because different thermometers had different scales. Then there was the puzzling question of what liquid to put in such an instrument. The scientists had to find something that would remain liquid at the temperatures which water boils and freezes. They tried everything from wine to olive oil, but these expanded differently and boiled and froze too quickly. A liquid metal known as quicksilver or mercury seemed to be the best material. The good thing about mercury is that it expands in a regular way over a wide range of temperatures. But this expansion is so small that it's hard to see. So a long, thin tube of glass would have to be made to register any changes. In 1714, along came Daniel Fahrenheit, an exceptional instrument maker and glassblower. He was the first person to blow glass thermometer tubes with precise and even dimensions. To match the precision of his instruments, he devised a new scale, the Fahrenheit scale. This scale was widely accepted. It had pure water freezing at 32 degrees and boiling at 212 degrees. About 30 years later, another scale was invented that neatly measured from 0 to 100. 0 was the freezing temperature of water, and 100 was the boiling point of water. It's called the Celsius scale, and today most countries have abandoned the Fahrenheit scale in favor of the Celsius scale. In the United States, though, we still use the Fahrenheit scale. There is one other scale made in the 1850s by the physicist Lord Kelvin. Kelvin started his scale at a point where all the heat was removed from a material. Kelvin called this point absolute zero, and it occurs at minus 273 degrees Celsius. It is impossible to reach a point that has absolutely no heat, but one place is very close to it. It's one of the coldest places in the universe. Where is it? Far off in deep space? Perhaps on Neptune, where it's so cold that the volcanoes spew ice instead of lava? No, it's a little closer to home. So is it Antarctica, deep under the permafrost? No, it's in England, at Lancaster University. Professors Pickett and Guénaud have built a supercooled fridge that removes almost all heat out of materials. Physicists use this super fridge to study what happens to molecules that lack heat. Down here, even the softest things are hard and brittle. Gases are as solid as a rock. On the other end of the scale, however, there doesn't seem to be any limit to temperature. Most of the time, we're not interested in the extremes of heat, but whether our coffee is hot or our milk is cold. And thanks to our scales of measurement, we can tell pretty accurately how much heat a material has.
Try this activity to complement heat. Fill a bowl halfway with hot water and fill a water bottle with cold water. Let each sit for 1 minute. Empty the water bottle and stretch a balloon over its mouth. Stand the bottle in the bowl of hot water. What happens to the balloon?